Hi and welcome to my long promised video on the Beast car's body design. I'm going to show how I use CFD to develop the shape of the body shell, and it's going to be a bit of a journey. There's some interesting designs in there, and there was some learnings that I came across along the way that I'm going to go through at the end. Before the end though, I'm going to show the detailed CAD design that I came up with, and there's some interesting features in there.
So back to the timeline, you might remember this from a couple of videos ago. It shows that between July and August, I plan to design my chassis and body, including doing any CFD. I decided to split this into two phases for the body design. So phase one, early on in that period, before I had to order the sheet carbon parts. The reason for that is I needed to make some key design choices that would affect the chassis design and the design of these sheet carbon parts. I also had to design the fins of the body so they could be ordered with the same set of parts. The second phase was pushed right back towards the end of that design period. It had to be finished just in time so that I had enough time left to actually make the parts, and there was some final CFD tweaks in there as well. So just a bit of a recap on the requirements for the body system. On the last video, you saw that I was going to aim to minimize the frontal area and the drag coefficient of the body shell, because as I showed, that's important for RC speed cars. I'm looking to have a balanced downforce across the front and the rear of the chassis, and it's obviously got to have space inside for the chassis, including having clearance for the tyres, which is obviously important for speed running, where the tyres might expand a little bit as they go faster. And the car should be tolerant of ride height and attitude variation. So by that I mean that as the car goes over bumps, it might go up and down, it might angle up at the front or down at the front. The body shouldn't be too sensitive to those variations so that it doesn't just suddenly flip up and take off the moment the front bumps up a little bit. It should have directional stability, so in a similar way, if it gets pushed offline slightly, it'll tend to pull itself straight rather than veer off even more. It should have a lighting system to give an increased range of visibility, and it should be manufacturable with the tools I've got at my disposal, mainly with 3D printing is what I'm envisaging for that. And it should obviously have sufficient strength and stiffness so that it maintains its shape during the speed run, and maybe could handle a small crash or two. That would be nice to have. So straight in then with the key question that I had to ask myself in this phase one of body design, and that was what form should the floor of my car take? What I'm showing here is the flat floor. So this is where the floor of the car, it's totally flat as you can see, and it's parallel to the ground. This is the easiest configuration to make because you can just make the floor from a sheet of material, and you can design it with similar ride height front and rear, which is more straightforward. The second most simple one is, again, a completely flat floor made from sheet material, but with it angled up at the rear. I know this is one that Rob of RC Man definitely advocates. He thinks this is definitely the way forward for RC speed cars, and he's shown that from practical experience. So I thought I'd try that with the CFD and see if that backs up his findings. Thirdly, I wanted to look at with the knowledge that a lot of racing cars do some quite funky things with their floor. Like, for example, they might have a diffuser shaped like the inverse of an aeroplane wing. So in cross section, it starts a long way from the ground, and then it gets closer to the ground, and then it goes away from the ground again in this sort of diffuser section at the rear. And they also have all these funky turning vanes. I was interested to see if something like that could be useful for RC speed running. Although I did have in the back of my mind that if I went for something like that, it's going to be a lot harder to manufacture than the flat options, either the flat or the raked. So yeah, this is just another image showing the underside of a Formula One car. These sort of turning vanes that try and take some of the air to the outside, but then some of it's going to go through this diffuser throat to give, the idea is to give low pressure underneath the car, which sucks it down onto the track. And finally, I was also seeing this JCB Diesel Max design, which in a similar way has actually got a shaped underfloor. It's got these little vanes here that take air in at the front and then send it out of the sides, which then probably creates like a vortex that goes down the side and aims to take air away from the front of the rear wheels, which would generate a bit of lift, which is obviously undesirable on a land speed attempting car. So those were my inspirations behind my early design exploration. Bit of a background into how I'm going to take the outputs from the CFD analysis. So one of the raw outputs that I take out of it is this total force Y, and that is effectively the drag force that's generated in the run. It also gives a total downward force and a total moment, which is basically the turning force around the rear axle. So in themselves, these outputs aren't particularly useful, but what I could do was by considering the input test speed, the input air density, frontal area measured from CAD, I could calculate the coefficient of drag, and the CDA value that I mentioned on my previous video was important. I could also calculate the precise amount of downforce at the front and the rear wheels, so I could get that balanced downforce that I was looking for, that I mentioned in my requirements. So let's go over to CFD then and have a look at those early results, and then I'll show them in a results table. So here's the first design with the flat floor that's parallel to the ground. The key thing to point out on these results is that there's this sort of light blue area on the top there. That means there's low pressure there, which is not good on the top of the car. That means it's basically being lifted off, it's trying to lift it off the ground. I mean, there is corresponding low pressure underneath, but it's fairly even really, which is maybe not ideal. You know, ideally you'd want more low pressure underneath and some higher pressure on the top to try and push the car downwards. If I put the streamlines on, those are looking amazing though. I mean, because it's such a nice teardrop shape, the air sort of smoothly gets parted by the car and then it joins back together afterwards, which is going to help reduce drag. Oh, where's it gone? Come back. There it is. Yeah, so next design then. This is the rake design. So looking at the pressure plot again, we've still got the same low pressure on the top and on the side there. But if we look underneath, crucially, there's this darker blue area underneath. This is an area of lower pressure, which is going to help pull the car down onto the ground. If I put the streamlines on, you can where it goes red there, that means the flow is going faster, which corresponds with the low pressure. We're going to see a common theme for all of these plots, that the tyres light up as an area of high pressure, but I found there wasn't really a lot I could do about that. So that's the flat bottomed one, and then I'm going to show the first sort of more funky shape design that I tried. So this one was taking that idea of like an underside wing into the design and analysis. So you can see there's a bit of a throat formed underneath the car. So it starts off higher, goes lower to the ground, and then it goes higher again towards the rear. Pressure wise, it's got a lower pressure zone under the car, maybe not the lowest pressure though. And in terms of streamlines, it looks even more perfect than the one we just looked at. So let's go back and look at the results table. So as we saw from the streamline diagram, the we're seeing some very low drag coefficients on these designs because the air just gets smoothly parted at the front and it joins together again at the rear, so it's causing very little drag. These are amazingly low values, so that's the good news. The bad news is that we've got lift at the front and the rear shown by these negative downforce values. So quite severe actually over the whole car. That's getting on for 8 kilograms of lift for the flat floor design. There's some promise definitely shown by the rake design that shows some decent downforce at the front, but still none at the rear, probably because of the design I've got going on there. And the underwing design showed I suppose, quite a significant improvement over the flat floor, but it still doesn't give much downforce at the front, so maybe not something worth pursuing given the complexity of making a car with that layout. So let's go on to the next things I explored, which were linked to the Formula One floor and the Diesel Max floor. So firstly, this is the design I decided to try, inspired by Formula One underfloor shaping. So you can see it's got like a vent that goes through from the front and out to the side, and it's got some cutaway behind the front wheels there, and then the underfloor sort of turns into a bit of a diffuser shape as it goes rearwards. So we've got quite a nice area of lowish pressure underneath there. On the upper side it looks the same as before, no great surprise because I didn't change it. And then the particle tracing looks nice. Yeah, it shows the flow joining together nicely like before, so it should have quite a low drag coefficient. It's hard to tell the actual benefit of the modifications that I made there. I think we need to look at the actual numbers to fully understand that. I mean, that's what I found throughout. The plots can look nice and look like you've made an improvement, but then it's the numbers that really matter. So we'll have a look at those in a second. Next, I'm just going to show, or before that, I'm just going to show this other option that I considered. So this is the one that was more inspired by the JCB Diesel Max. So it's just got the vent that goes from the front out to the side, and it's got a little shield bit that goes in front of the rear wheel. And although another big change I made on this model was that I sort of thickened the rear edge of the shell and had a little flick up there to try and get some rear downforce, probably at the sacrifice of some of the low drag coefficient. So it'll be interesting to see how that performs. Particle tracing on. You can see there's a bigger area of turbulent flow at the rear of the car from where I've thickened it up, so the flow doesn't join together quite as nicely as before. And you can see that there's an area of a slightly stronger green colour there, which is good. That's high pressure, so that should be giving us a bit of downforce there. Look, what about the underside with the little vents and everything? It seems to be taking a bit of flow off the rear wheels, which is no bad thing. So that's going to, any high pressure on the rear wheels there, it's going to be trying to lift the wheels off the ground. So if that can be reduced, then that's good. But disappointingly, what I've done, it didn't really make any difference to that high pressure on the front tyres. As I mentioned before, I really struggled to find anything that had an effect on that. So yeah, let's look at the numbers for those two options. The F1 style underbody, that showed quite a high increase in drag coefficient actually. So that change did come at a quite significant cost. It did show some promise in giving a bit more front downforce over the flat floor options, but not as much as the raked floor. And the Diesel Max style floor, that again went up in drag coefficient, but then it did have that new rear end design, and it did help the front downforce, and more significantly the rear downforce was showing some sign of improvement, although this is actually probably too much downforce. We don't want 8.5 kilograms pushing the car down at the rear. So I might need to just back off on that a bit. But you know, it's easier to back off on it than try and find it from nothing in the first place. So let's look at the next couple of design options. Let's talk about splitters. You might be wondering why I haven't mentioned these sort of protrusions from the front of the car that are quite common in RC speed running, and that's because I tried them on my first speed car, the Cone Mark 1, and I had to take it off pretty much straight away because it was scraping on the ground, causing extra drag, and it actually was catching on some imperfections on the runway surface and nearly causing the car to flip over. So I was slightly burnt by them with that. And also other observations I've got from other people's cars, I've seen where if the front of the car gets bumped slightly and they get a bit of air underneath them, then the car can often flip backwards and go flying basically. And I do wonder if having that front splitter that's so close to the ground is partly the culprit for that. So basically, early on with the design of this body shell, I decided to make the choice to have a slightly higher ride height at the front of the car than in the area of the wheels and tyres. And early on, I had I think a 10mm ride height at the closest point, and an extra 10mm to the tip of the nose there to just give a bit of an allowance for any surface imperfections. And maybe the car getting bumped at the rear and causing the nose to come down lower, which I think was happening with my Cone Mark 1 car. So yeah, that explains my design choice there. I did try adding a splitter onto some of my designs like I'm showing here, but I found it didn't really have any benefit, probably because it wasn't close enough to the ground to do what it needed to do, and take some force from the air being pushed down from the body shell, and turn that into downforce. Okay, so I'm not going to show the results for this one because, as I mentioned, it didn't really give any benefit. But I am going to show results for this one. This one represented quite a good step forward. So this coincided with the optimization of my chassis layout. So I was able to reduce the width and length of the chassis, which correspondingly made the body shell a little bit smaller. And because of that frontal area reduction, the CDA value, which I mentioned on my previous video, is very important. That goes down a little bit. So that was a nice optimization. I also decided to compromise my front raised ride height that I mentioned a minute ago by 5mm. So it's still got 15mm clearance at the front in static condition. But what that did, it actually helped a bit of front downforce. So it shows a good area of low pressure here, which helps pull the car down onto the ground at the front. And at the rear, you can see I'm showing that flick up design from earlier. I reduced it slightly, as in slightly less flick up, to reduce that 8 kilograms of downforce that I found before. So this one I found gave a good step forward, as I think you'll see from the figures in a second. I decided to check though with a flat floor again with the other optimizations whether that would still be a viable option, because as I mentioned at the start, this is the easiest design to manufacture. So this is the flat floor parallel to the ground. The results show, you can see there's a lot less low pressure towards the front there, and there's more at the rear, because that's because the rear is acting a bit like the diffuser. So the throat is now there, so that's where you get the low pressure, which is not ideal. It's now out of balance. It's going to have too much downforce at the rear, not enough at the front. The final run I'm going to show here is the same as the optimum one that I mentioned a second ago, but with the front raised another 5mm. This is actually an experiment to test for that attitude variation. So if the front was to get bumped by 5mm, that's what I'm testing here to see how sensitive it is. So let's look at the figures for those. So the results from the runs we've just seen are added to the table. So the optimized one is here. Its CDA value is actually reduced from the previous runs because of that reduction in frontal area, even though the drag coefficient itself has gone up a little, probably because I've managed to get a bit of extra downforce out of it. The downforce itself is very nicely balanced, so it's got almost the same downforce at the front and rear, which is just what I was looking for. And my check run where I took this design and made it have the floor parallel to the ground, that did show again that that flat floor idea isn't desirable because the balance of downforce goes more to the rear. So that shows in my mind that the rake design is the way to go for my speed car. Finally, the run I did with this design, but with the front raised by 5mm, that's why it's got the stars there, to test that for that attitude sensitivity. It shows a massive reduction in front downforce. In fact, it goes to nearly 5 kilograms of lift on the front. The rear stays pretty much the same, but I found this a bit worrying. So this is something that I need to work on in my phase 2 development. So at this point, I decided to call it a day for phase 1. And it meant I could go for a flat floor design, which was easier to manufacture. I say a flat floor, I mean a flat floor that's then raked, and I could send the fins off also for manufacturing. So I'm pausing it there, and then I'm going to work on the attitude sensitivity on phase 2 of the development.
Hi, I've got into editing and realised I've got just too much material to go into just one video, so I've decided to split it into two at the end of the phase 1 that you've just seen there. So the next part, it's going to go obviously through phase 2 of the CFD development work, show the weird designs that I mentioned that came up along the way, and go through the CAD development of the final designs. So keep an eye out for that coming out very soon.